I'll draw it and attempt it, and you can tell me if the picture looks similar. So let's try that. Okay. Oh gosh, this thing is. Okay, so let me just create one and call it fluids. I do not know where any of these things reside, so. Okay, so was the curved gate like this?
Yeah.
With the water back here?
Yeah.
Okay. And so, let me redraw that. It looks kind of funny. Here, hang on. Okay, so as long as I know, I can do a better job of drawing it. So, it kind of was like that. Did it have a hinge right here?
Yeah.
Okay, and then we're assuming that the thing is no leak. And it has water back here on the left side and air over here. Air over here. And there's some sort of structure here. Some sort of structure here. And it sits like that. Oh, here. GE. Okay, so it's got a hinge. It's got that. It's got water. So in a gate like this, the way you approach it, shoot, I've got these things all in the way, but you know what? I can do it like this. I'll erase this no leak. And then I'll make this yellow like it doesn't exist, so to speak. So you go into here, and you get this kind of pseudo non-volume here that just sits with air, but if you took some sort of yellow substance that weighed exactly the amount of water, or whatever the substance is, whatever the gamma is. So if you took a brick of yellow stuff that has the same gamma as the gamma back here, and then you took another one and you made another blob. So these are blobs that if you could imagine that you could put in here and replace, this would have the same gamma as that and with that. So if somehow you could extract instantly the gate and replace it with two funny looking shapes that were solid, that were the yellow here and then I guess that's pink or maybe that's purple, then the hinge would be gone. I mean, the gate would be gone, and basically what you would be doing is you'd be finding the resultant forces. But it turns out, if you took the centroid of these two, that would be the weight, that would be the weight. So essentially, to off balance that, you gotta imagine that the water puts back a force that's exactly like that. Now, the other thing is this is a concrete structure, so it's not moving anywhere. So you've got a force distribution pushing here that doesn't do anything. It's just completely held by this structure. But then, if you did this, okay, this looks like a strange thing to do. Uh-oh. Oh, that's bizarre. Well, it moved my, here, let's try this. I don't know why it did that. Here, zoom way down and zoom way up and slide over, slide up and see. It did move that blue line. And it moved this. Well, let's see if I can fix that. So what I was trying to do, I was trying to do something that, okay, let's see if I can fix this. How am I going to do this? I can do that. Okay, well that moves that, but that doesn't move the other. Ah, there we go. Fix that back again. Okay. So the reason I was copying this is because I was going to do this and copy it to right there. And then I was going to go back and draw as if this were the force being pushed to the right. So now what you've got is, if you look at it from that standpoint, you've got, I don't know if I'm being confusing or not, but you've got a gate. Sits here like this. You get a force that's pushing up right here. Another one that's pushing up right here. This one can be broken into two forces. One that comes directly from the triangle. Okay, so this one will come directly from the triangle, and this one will come directly from the square. So if you think about it, you got one right here, and then you got one 1/3 down. It's probably maybe a little smaller. The gate doesn't weigh anything, so all this will, some of the forces will tell you, in the X will tell you that has to offset those two. And the sum of the force in the Y will tell you this one has to offset these two. And so did it ask? It asked for the horizontal force and the vertical force, right?
Yeah.
Okay. So the vertical force will be these two added together, and the horizontal force will be those two added together. Then, if you wanted to, you could do something interesting. You could sum the moments about this hinge point, and you know the moments have to be zero because it's not moving. What you find out is that there isn't an applied moment, that these do cancel out. And the reason they do, and this is why there's curved gates on all these bridges. If you go over to Lake Darnell at the spillway, you'll see this. If you look at an actual pressure diagram, okay, it linearly varies and increases as you go down in the depth. I'm trying the best to take my time. So as you go deeper in the fluid, pressure gets a little higher. The force diagram is perpendicular. So if you want to know what the force at this particular point, you look at it, you take a tangent right there, the normal goes in this direction, and in fact, that's dictating the, so if you take a normal to that surface, all these surface normals poke out like that. And so what you find out is the line of action from each one of these points passes through that hinge. So no fluid force is producing a moment about that hinge. Now, if you move the hinge somewhere else, it will. So if you hinged it right here, yeah, you're going to have that. But if you hinge it about a perfect circle, or this is a radius like this, they don't. They don't produce a hinge. So, I mean, it doesn't produce a moment. Which means if you're going to open that gate, and the gate weighs nothing, then you just pull it a little bit up with like a 1 pound force or a 0.0001 pound force, and it actually should move up. It should open. So technically, legally, it doesn't require a force to open that gate if it doesn't have any weight. Now, of course, there's no such thing as a weightless gate. So if you go over to the and take a picture of that, what you'll find is, those gates do weigh something. They have some weight out here. And so to offset it, to open it, all you're doing is offsetting that weight. Or you might be putting a torque here to open it. More than likely, that's what you're going to do. Instead of pulling at the edge, you're going to put a torque on the little part to open it. So if you look at, let me see if I, let's see. No, I don't know. Let's try that. Smart gate. Okay. Okay. I clicked it. Oh, here we go. When was this? 2013. Mechanical electric design for lock and dam operation. I don't know if this has any pictures of any of those gates. A lot of this will probably be regulations and stuff. Why is it not going down? There we go. Let's see if they are. They may not have pictures of the overall configuration of the gate, but I know I can find it somewhere. The reason I did Army Corps engineers, they're kind of in charge of it. Okay, gate. Come on. We'll just imagine if we keep going. If we see something that looks like a curved gate, we'll stop. Wait. There's a little bit of what? A little bit of a curve right there. So they're looking at the overall structures. They're trying to figure out. There it is. There we go. There's a drawing of some of them. So there's kind of your curve gate. Load, free body diagram, wire rope, and chain hoist. So, it looks like they got a chain. It sort of picks it up that way. And then this one, well, but the T goes towards a thing that way. But all the gates are going to be curved in order to cut down that. That's a straight on look. That's not a side look. So you can't really, that's not really, they're out there. I think the thing is already gone. Okay, wait. I can't tell what that was. Anyway, now these are different. Okay, so here's the different full scale old stem dead wicket. That, you can see hydraulic cylinder holding the water back there. So, but the ones you have over at Lake Darnell, they're curved gates that can be opened. Roller gates, there's a roller gate. Floating drum. Okay, so that's an interesting, there's your hinge one. Floating drum. This part to the lower. Okay, so there's all sorts of things, but a curved gate's kind of nice, especially if it's curved and it's made as a circle. Anyway, I got distracted there, but there probably is some better pictures down there somewhere. But you can see there's a lot of different types of, and these forces can be massive. So you really need to have stuff that's pretty reliable, because if things break, that can cause a lot of damage. Is that in St. Lawrence River? St. Lawrence Seaway. So I think that's way up. Oh, they even got stuff from Germany in here. So there's a whole science behind all this, as engineering as well. And with seawater rising, Maybe it'll be more important than we think. I don't know. Does that answer the question? I mean, that was a long answer to it. I don't know. I don't have any idea what that is. Oh, I'm not gonna log in. Oh. I wouldn't think the Army Corps would have that. But I guess they have their own. So does that sort of answer it, kind of?
Well, the one that I keep getting wrong is the one where it says, the Y direction.
Oh,
I'm getting, the answer that it says, it just says like 1 point something, and then I'm getting like a 4,000 or something like that normally.
oh, okay. Well, here, let's see. What is going on here? Okay, let's try this. Okay, so this is just, okay. Well, I mean, so are you doing this where you go in and, so really, on this, you gotta figure out, the weight of that column is gonna be, okay, so if you do it per unit into the board, oh shoot, anyway, that was supposed to be so it's kind of like that. So the weight is equal to gamma times the volume. Gamma is whatever this height is, from here to here, and then whatever the radius is, and that may be you with the symbol there. So that's basically the weight of this, and this will be halfway, radius over 2 be halfway over. This one, the weight of that one would be nothing but gamma times the volume here, but a different volume. Gamma times pi r squared over 4, because you only got a quarter circle there, and times if it's done for 1 foot there. So if that's 1 foot into the board, I think I've made it that way.
Yeah.
So that's the weight there. So the weight total should be this one and that one put together for the vertical. The horizontal one should be, okay, so if you take this, we'll give you that. The pressure at that point should be whatever the height is to that hinge, height to that hinge. Gamma is the pressure there, and that pressure is applied over the total area, which is, this distance is r. So you take that whole r, and that's pretty much, here we go. Let's see if I can do a circle right there. That's pretty much what that is. H gamma times r. So that H is here, which is supposedly at the hinge level. Then you got this one, and this one is from the triangle, and that triangle value should be, okay, now you don't care about how deep it is because you're taking this as if it starts. So what you're doing there is you're taking a triangle, the area of that triangle be the R, and of course this is for 1 foot into the page. R, oh well, you have to have that gamma. And then, okay, if you just said gamma times R, then that would be, let's see, I could do this and then erase it. Okay, so that would be, okay, if I don't lift my pen, the area of this right here, the gamma times R times, okay, gamma times R be the value at the very bottom. Now that's the pressure times the area, which is R by 1. So it'll be another R, but before I do that, let me take that off. By R by 1, I guess I could do R by 1. But it's a triangle, so you have half of it. Okay, let me do that again, make sure that makes sense. So what we're saying is, essentially, you got a curved gate, sits here like this. There's a person standing back here, looks at it. From this perspective, what he sees is this. Okay, so that's what he sees, is he sees it in a kind of horizontal plane. So here's your big concrete part that's doing itself. You got a load that sits here. Now, two ways you could find this. You could find it by force is equal to gamma h bar A, which would be the h bar to that location. Or you could break it into two parts, and that's kind of what I did. Okay, let's erase that, and let's say we're going to break it into two parts. Okay, so we're breaking it into the part here, which I'll call red, the red. This happens to be R. This happens to be H. So the pressure right there is gamma H. So if you consider that to be executed over all of R, did I put the R up there? Gamma HR, which is right, gamma. Okay, let me use the pen. Okay, gamma HR. So it is that pressure put across a gate which is R tall and is 1 into the board. If that's the case, then the equivalent load, if I could redraw it over here. So here's the gate. I'd have a force right there that would sit right in the center. That would be gamma H R, or gamma or H, or whatever. That's from the uniform portion of the load. If I turn around and then I start looking at the triangular portion, this down here, that distance alone is gamma times R. Now, if I want to take a uniform load, being that this is the case, and I'm looking at this, I'm trying not to pick the pen up, and you'll see why in a second. So if I had a uniform load here, then that would be gamma R, which that's because that's what this is, times R, because that's what it's applied against. But the equivalent load there would be, here, put it right over here. It's going to be a third up from the bottom, or this distance will be R over 3. But this value will be gamma R. That's the value at this from here to here. And then it's applied over R, but it's a triangle. So half of it's gone. Does that make sense?
Yeah, I think I understand it now, because the one that I kept missing was the Y direction one a lot. And so I think, because I don't think I was adding them together. I was just doing this bottom part right here where.
This part right here?
Yeah.
Okay. Yeah, and if you think about it like this, if you had two pieces of solid that weighed exactly the amount as far as gamma, that weighed the exact amount per volume of water, and put them there, if you just put the pink part down there, the water will push it up, it'll float. So you got to put the heavy part on top of it. And hopefully that, so if that answers your question, then that's good. And I guess you'd have to go back and. Surprisingly, the hardest, it's not hard. It's not outside of the realm of reality, but the one with the biggest tripwires, how about that, say, is this fluid static section. Bernoulli's equation and some of the momentum and some of the pipe drop, doesn't have things to trip you up as much. It seems like fluid statics trips up, because it's tricky because you say, oh, okay, it's just statics again. And then you're just kind of, oh, okay, I won't, but then you know, it just does, it trips you up a lot. So, okay. And so I guess it's 12:30. What about anything else? I really didn't have any lectures prepared or thinking about anything yet. I was going to go back and do that with a pump and put it in a system. But maybe I could do one later this week, just ad lib and send everybody an announcement, say I'm going to do a lecture this period and do a pipe with a system with a real pipe on it. I mean, a real pump on it. So, anything else that was?
I started applying a little bit. I think I should go over it a few more times by myself first.
Okay. Okay. All right. Well, then what I'll do is maybe what we'll do, I tell you what, because if I prep it here, I got to figure out how to send. I know what I could do. I could prep it, send a copy to myself. So what I was thinking is okay, so generally pumps are kind of drawn like this, and you have a inlet that draws in. That's the way they're kind of drawn on the diagram. However, I kind of goofed that drawing up, didn't I? Here. So water is generally drawn up through a system, and say you're doing a solar water heater. So you're drawing it out of okay, so here's your swimming pool. And it dumps the water into the swimming pool, and then it draws it out of the swimming pool. So here's your swimming pool. This is an awful drawing. So here's your water coming out, pouring into your swimming pool. This is your solar panel. And then, you know what we'll do? I'll concoct the problem, and then what I'll do is I'll solve it. I might wait till next week and solve it, but let's say this is like, I don't know, you can go buy, how about 1.5 inch PVC, and we'll have to look, let's say, or maybe let's say it's 1 inch PVC. The reason I'm stopping to think about this is that, you know, what do you do with a solar panel? Well, we'll do this. We'll say it's a 1 inch PVC pipe that's internal diameter. And then it comes out and it splits and it goes back and forth in like a black background to absorb heat, and it comes out, back out. So we'll say this is the equivalent of 50 foot of long of 1 inch PVC in some sort of arrangement that's like, you know, like some sort of cabinet that, well, you could just paint it all black and say when it gets in there, the pipe just goes back and forth and it absorbs the heat as the sun lays on it. And so we'll just say it's the equivalent of 50 extra feet of PVC going back and forth, maybe 150 feet here. And then we'll say this part right here, the length is maybe 20 feet. And then we'll say this is 50 feet. And then we'll say this is another 10 feet. So essentially, what do we have? 150 feet, 50 feet right here, 20 feet, and 10 feet. So we've got, what, 230 foot of 1-inch PVC, or something like PVC, something that is smooth. Inside here, this section is painted black, or somehow. Now, we can get in the details and say, but that's heat transfer. The details might be, you can collect so much heat in there. If you ran the pump too fast, the temperature of the water is not, okay, so you got the temperature of the pool. This would be temperature pool plus like a delta T from, not time, but delta T. And the delta T is as a result of the sun heating up the water as it goes through if you pump the water too fast, it's not resident in there long enough to get much of a delta T. And so there's probably a perfect flow rate. That's left to heat transfer. But what we're going to do is we want to size this pump. So what we're going to do, and we'll do this next time, we'll size the pump from real pump diagrams. And so we'll pick up this problem, size it from a real pump diagram. So now let's go find some real pump diagrams. Okay. Oops. Okay. Gosh. Pumpkins, okay. Okay, so there's all sorts of these things. And what we'll do, we'll even go and construct a pump diagram. So here's how we're going to do that. Let's see. We got a few minutes, so let's see if I can do that here. G-R-A-I-N-G-E-R? Oh, here we go. Okay, yeah, I know. Okay, so here. I don't necessarily want a submersible pump. How about this one? Okay, and then booster and pressure. We're just gonna do straight self-priming. We don't need that. Straight high flow pumps. But do we need high flow or do we need straight? Let's just do that. Okay, so all right, so let's see. There's a bunch of different. Hey, they come out with size of 1 inch. Oh, that's funny. So here, we'll just. What happens here? Click that. View product details. Go down here. Let's see. He does not give me technical. Oh, that's feedback. I don't need that. He does not give me maximum gallons per at the head, 59 at 10 feet ahead, maximum pressure. So he doesn't give me enough information to really create a nice pump curve. So let me go back, and I hate to make a selection based upon the fact that, I can't create a pump curve out of it, but here, let's go to this one. Let's keep looking around till we get enough. Maximum, so it's 180 gallon per minute at 66 feet ahead. But I need to now know what is flow rate for a smaller. And some of them, best efficiency is 120. So I could, 125 gallons per minute. I could, minimum gallons per minute. Okay, wait. Engineering data. Let's see what this looks like. And you're going to, boo, that's no good. I want, okay, here we go. There we go. There's the first evidence of. There is an actual official pump curve. Now, how many of these do I have? You can go all the way down to 3 and some sort of 16ths that I can't really see. Well, 13 sixteenths, all the way up to 6 inches, almost 7 inches in diameter. We're going to use this one because, I mean, it's there. And so we're going to come in and just start going through these. So what I'll do, I will use this. I'll do a copy, come back to my thing. I'll put it in here as a text insert, like draw. I think if I just hit a spot and just do a Control V, there we go. Now I can do a draw, and maybe I can move that. Maybe I can't. It doesn't matter. If it's in the way, it doesn't matter. But I know if I hit a Control and click it, it'll go back to the curve. So, these are kind of overlays, and they're kind of bad and good because you can see these are operating ranges for the pumps, and we'll talk about that. But some of these are hidden. So in other words, if you wanted, 200 gallons per minute and the total hit of 40, you're probably going to want to either be using this pump or this one. Or sorry, that one. If you're over here and you need 400 gallons at like 20 foot ahead, you probably need to be using that one. So it gives you some overview, and then you go down to the actual pump curve. So you notice the diagram has a sort of arc down to the right, and it covers all this. Well, this is a zoom in of each one of the different pumps. And so what we'll do next time, we'll come in, we'll actually we'll pick one of these types or groups of pumps, we'll pull it off, we'll copy it, put it on there, and then we'll calculate the system curve and to figure out where it actually ends up at. Some of them are thin, like this one, it's pretty thin. We'll look at these, which are the efficiencies. So there's your efficiency of the different things, or those numbers are. So that's an efficiency. The best efficient operation for this pump is somewhere in this region, 72, 73%. If you operate back here, you're wasting a lot of energy, and you probably should go get yourself another pump to operate there. You can operate and move past that region because obviously when you turn on your pump, it's pumping nothing. So it's going to be over here at 0, 0. And so you're going to move across this point to a steady state somewhere. But what you want is you want the highest efficiency in operation. Like there's one. That's kind of interesting. Its most efficient is right here in where about that 68 sits. So moving, about 140 gallons per minute with the total dynamic head of somewhere around, 55. So that's the best operating point for that. Now he's also got these 20 horsepower lines, and we'll verify this. This 15, this 10 horsepower kind of funny line. That's not really a line. It kind of wiggles. 7, and I think it's a half. 7.5 horsepower, 5 horsepower. So what we'll do is we'll verify this so you see where those come from. Look at the efficiencies. kind of try to get an understanding by backhanding our way through the whole system. So just most of this stuff on these Granger things, where did it go? If I go back, okay, go back. It doesn't go back. What? Oh, wait a minute. Is this? Oh, okay. I had it here, and then it opened it in the other. So most of these pumps should have some type of diagram like that for an engineer to actually use. You don't just buy a pump and just put it on a line. You'll find that it is the most finicky thing you could ever imagine. You buy a good pump and you think it's going to work, it might not do a thing. Or it might just bubble your water out and not give you anything. So these are very finicky little systems. So we'll run through that next time, because that's, I think, I've tried to put something like that on the final, but it is not a real pump. I think I just made up my own diagram. So.
Is this dynamics?
Yeah, this is dynamics. So we're talking about pumps.
Sorry, I've not attended all semester.
Oh, yeah, you didn't? Okay, so here's some pumps.
Isn't that related to conductance somehow?
You know what? Hey, so this is cool. Here's the part I like about it. So pumps are like circuits.
They are. They're just like circuits.
Yeah. So, you get this is cool. This is the part I love. So if you look at delta, that's supposed to be a delta. Over current, you get a constant current voltage source looks like that, without that part right there. Constant current source looks like that. Real pump looks like that. And that's just what a battery does. If you got a 12-volt battery and you short it, you don't get 12 volts out of it. You burn up your short, though.
You get a big voltage drop inside the battery.
Right, exactly. And that's what happens. That current draws it dead. So pumps behave exactly the same way. As a matter of fact, and this will be delta P, and that'll be the flow rate.
Look at that.
And so what it is, delta P is equal to some constant minus, or C1 minus C2 Q squared. That's what they usually model it as. And it's perfect. It works. It's not perfect. It doesn't perfectly line up with the curve, but it's pretty close. And for engineering that are using sizing pumps, it works pretty good.
Close enough.
So, so circuits. I'm teaching circuits.
You're teaching circuits.
That's
like circuits too.
Yeah. Well, is that circuits too?
That's like circuits 1.
Circuits 1. Yeah. Yeah. That's all it is. Nonlinear circuits 1.
You know what's interesting though, when you do like kinematics, do you do Laplace at all for dynamics?
No, I don't. I'd love to.
Oh.
I'd love to do that, because Laplace and then Z transforms, I love that stuff.
You could solve all the second order kinematics.
Yeah, you could do all sorts of stuff with that. But
that's funny that you don't, because they save that for control systems.
Yeah.
They make you do all the second order dynamics and control systems.
Uh-huh.
Why don't you do that dynamics?
I don't know. Well, because I think people might get mad at me.
People get mad when I introduce it in circuits.
So,